Hello, and welcome to this pre-recorded event for Design and Technology Product Design Resistant Materials. To help you get the most out of this feedback, you may want to have the documents shown on the slide at hand, as they will be useful for reference. As a reminder of requirements in the 6RMO1 course, students must produce a portfolio of creative skills, which is divided into 3 distinct sections: product investigation, product design, and product manufacture. In product investigation, students must select a product that contains at least 2 materials and is manufactured using more than one process. They are required to investigate the selected product under the headings Performance Analysis, Materials and Components, Manufacture, and Quality. Students, under teacher guidance, have complete choice in selecting appropriate products for investigation. Work can be presented in either A3 or A4 format. In performance analysis, students are required to write a specification for the product under investigation, using the headings Form: why is the product shaped or styled as it is? Function: what is the purpose of the product? User requirements: what qualities make the product attractive to potential users? Performance requirements: what are the technical considerations that must be achieved within the product? Material and component requirements: how should materials and components perform within the product? Scale of production and cost: how does the design allow for scale of production, and what are the considerations in determining cost? When analyzing a product under these headings, students should justify statements to say why they are important to the product, and they should also say how these needs have been achieved in the product. Students can investigate any product of their choosing, as long as it consists of a minimum of 2 materials, and has been made using more than a single process. As well as writing a specification for the selected product, students must identify a similar product and compare and contrast the two, using the specification headings described previously. In order to compare and contrast effectively, students must identify differences in the 2 products, in order to discuss relative design features to determine which meets a specification point best. So it is important that the similar product is not too similar. Where products are too similar, form, function, user requirements, performance requirements, materials, etc., will be almost identical, which leaves little opportunity to identify differences and to compare and contrast. The product pairings shown are so closely related that no effective comparisons can be made. The products shown on this slide are similar in that they fulfill similar needs, but they are different in the way these needs are achieved, offering lots of opportunity to compare and contrast under the specification headings. One of the images of products shown on this slide was gathered from the internet, and the other one was created using 3D CAD, both of which are inappropriate to the requirements of product investigation, because the products are not physically available to the student to analyze realistically. Requirements cannot be met by using photographs alone or virtual images. Products should be available for students to examine appropriately, which is important to the other elements of this unit. In the next part of product investigation, materials and components, students are required to identify the materials and/or components used in making the product under investigation. Only the original product and not the similar one must be considered in this section, and in the sections following. The similar product is only appropriate to performance analysis. Because products will vary in the variety of materials and components used, it would be unfair to ask some students to investigate all materials used in a complex product, such as a motorized lawnmower, while others looked at the materials used in a plastic clothes peg or a throwaway ballpoint pen, which meet the minimum requirements of 2 materials. Taking this into consideration, students are encouraged to identify only 2 materials and/or components used in their selected product, and to investigate these. When identifying properties, mistakenly this task is seen by many students as an opportunity to list everything they know about a material without any selectivity or justification for use. A moderator does not want to know that a material is a good electrical insulator when it is being used for an underwater application, or that mild steel contains less than 0.3% carbon without some reason for presenting this information. When material properties are given, these should be justified to say why they are important to the design needs of the product, and should not be part of generic information that could apply to any product. Having identified 2 materials and discussed advantages and disadvantages, students are required to suggest 1 appropriate alternative for each of those materials. Unfortunately, many alternatives given are almost identical, especially where plastics are concerned, such as ABS and HIPS, or PVC and polypropylene. Part of the reasoning behind this section is to encourage students to use their knowledge and understanding of a wide range of materials when applied to products, giving relevancy to their Unit 2 studies, and hopefully creating more interest. As part of this section, students should consider the environmental impact of extracting and processing the raw materials used in the product, and to also consider disposal. Often responses are limited to recycling and generic statements regarding air pollution, when more detail than that is required. The slide shows 2 different responses to environmental impact. The first describes only negative effects, while the second shows how, once iron ore has been mined, leaving an ugly scar on the landscape, this is turned into a lake over time, supporting wildlife and biodiversity, and perhaps improving the environment. In summary, students must identify 2 materials used in the manufacture of the product, and use advantages and disadvantages to describe specific properties of the materials to justify their use in meeting the design needs of the product. They must also suggest 1 appropriate alternative material for each of those identified that could be used in manufacturing the product, describing why each would be appropriate. The environmental impact of extraction, processing and disposal of the materials used in the product must also be discussed. The next task in this unit is to investigate the manufacture of the product by identifying and describing 2 commercial processes used and suggesting 1 appropriate alternative for one of the processes. When identifying processes, students should use advantages and disadvantages to justify their use in meeting the design and manufacturing needs of the product. Generic statements that could apply to many other products should be avoided. The slide shows a well-presented sheet describing injection molding and an alternative process, but all of the information is generic and not focused on the manufacturing or design needs of the product. Perhaps a more appropriate response would have been to point out such things as the need for the product to have a complex, thin-walled shell that required screw sockets integrally molded to receive fixings, so that it could be joined to the main body, and the only way of achieving these features would be through injection molding. It is often difficult for students to suggest an appropriate alternative manufacturing process, especially where plastic molding is concerned, and this can result in inappropriate processes being suggested. Where there is no real alternative to a process such as injection molding, it is acceptable for students to suggest a process that would be appropriate if a different material were used, as long as they name the material. It should be borne in mind that any processes identified or suggested should be those used in commercial manufacture. Students should describe the environmental impact of using the manufacturing processes identified, which will be different to the effects described in the previous section relating to materials. The final section in product investigation focuses on quality. To meet assessment requirements, students must describe a range of quality checks carried out during manufacture of the product, specifying what the checks would be, how they would be carried out, using what equipment. A quality assurance system should be designed for the product, and this could take the form of a flowchart, for example, using headings such as preparation, processing, assembly, finishing, and after-sales. Commonly, responses are submitted that describe what quality control and quality assurance are, but what is required is a range of realistic quality checks, as described previously, and a quality assurance system focused on the product in hand. As part of this section, students should identify 2 or 3 relevant standards and explain how they would influence the manufacture of the product. It is not enough to simply identify some standards. Students must say how they relate specifically to the product and its manufacture. In product design, students are required to submit at least one design task appropriate to AS levels of response that demonstrates their design competencies. They are encouraged to be as creative as possible, and to support this, there is no requirement for the designed product to be manufactured, which means there are no constraints placed on designs through the limitations of resources found in centres. Students have the option in product manufacture of making what they design or of making something different. In the course of designing, students are expected to produce a range of initial design ideas, accompanied by technical annotation, a review of design ideas based on product specification requirements, and development of designs into a final design proposal that includes enough details to allow a skilled third party to manufacture the intended product. Students, under teacher guidance, have complete choice in selecting appropriate design briefs. More than a single design brief may be undertaken, depending on what skills a teacher wants to develop in students. But most students pursue a single design task. Work should be presented in A3 format. The starting point for the product design exercise is to present some measurable design criteria to use as a guide and reference as designing progresses. The example shown on the slide is of a very comprehensive set of information, which is unnecessary and carries no marks. The design brief and criteria can be set by the teacher and should consist of 4 or 5 performance-related points that can be used to check the viability of ongoing designs and to evaluate the final design proposal. There is no requirement for anything more. The example of a design specification shown on this slide consists of succinct technical design criteria that can be used as an evaluation tool. It is important to produce design criteria that can be followed throughout design and development to guide designing, and to avoid superficial and simplistic evaluation of the final design proposal. When designing, students should present a range of design ideas that are detailed with technical annotation to describe possible materials and processes that might be used in manufacture, if the design was taken through to production. It is important to include graphical details to support annotation, where statements specify that component parts adjust, swivel, slide, and so on. This slide shows a range of simplistic designs that lack detail beyond very limited and superficial technical statements. There is no attempt to show how proposed products might be constructed, and information on materials is generic. This example of design sheets is in contrast to the previous one, and is full of technical detail of design subsystems, illustrating both graphically and through annotation how proposed products would be constructed and made to adjust, rotate, or affix to surfaces. During designing, reference should be made to design criteria to check that designs are meeting the starting points, and statements should be justified to say how or why points have or have not been met. This slide shows a poor choice of design task. Designs are very similar, materials and processes are also similar, and the range of design opportunities is very narrow. Designs are little more than body styling exercises. It is important when setting a design brief that it is appropriate and will allow students to display their abilities and give access to the full range of marks available. This slide demonstrates a poor approach to designing. Simplistic designs are accompanied by copious amounts of annotation, which is technically correct, but there is no attempt to explore graphically how subsystems would operate. It is not expected that all students will have high-level sketching skills, but at this level, students should be capable of communicating detailed ideas graphically. Some students present work under the Blue Sky heading, where they design products using concepts that are not available at present, or employ technologies that are complex, advanced, and not easily understood. The example shown is a wrist communication device, where the student does not have to be concerned about the control technologies, but must design a product that uses them, specifying materials and processes and producing a range of designs, just as in any other approach. When initial design ideas have been produced and reviewed against design criteria, one design should be selected for development. This may include design features from other ideas, but only one full design idea should be developed. Development means change, and this should be illustrated by students through their ability to bring together the best or most appropriate features of their design ideas into a coherent and refined final design proposal that meets the requirements of the product specification. There must be evidence of the developed design having moved on from an original idea through the results of review and evaluation. It is not acceptable to simply take an initial idea and make superficial or cosmetic changes to it, and then present it as a final developed proposal. Students should include as much detailed information on all aspects of their developed design as possible, as this is an opportunity to show knowledge and understanding of their design and make activities. This slide shows how an initial idea has been further developed and refined into a final design proposal to match design criteria set at the beginning of the design task. Development does not have to take the form of dramatic changes in the shape of a product. Adding features and technical details are also acceptable as development. However, just showing construction details of how the product would be assembled would not be worthy of high credit for development. Detailed development of component parts is acceptable evidence in this section, as shown in this slide, where 3D CAD modelling and a detailed working drawing combine to present the final design proposal. Modelling is an important aspect of design development and should be used to test features such as proportions, scale, mechanical details, subsystems, etc. Modelling can be done through the use of traditional materials or through the use of 3D computer simulations and rapid representation techniques. Evidence of real-world modelling should be presented through clear, well-annotated photographs. There should always be a reason for modelling. It should not be used for presentation purposes or for cosmetic reasons. Development should produce a clear and detailed final design proposal that includes technical details of materials, processes, techniques, fixtures and fittings that will be used during product manufacture. There should be enough information present to enable a skilled third party to manufacture the product. The final developed design proposal should be evaluated objectively against the points of specification to justify the design decisions taken and recorded in detail by students. Communication marks are gained for evidence of effective communication using a range of media, including ICT. It is not the variety of communication techniques that achieve marks, but the skill and precision in using them to convey design ideas and their development. The range of techniques might include freehand sketching, pictorial sketching, formal working drawings, digital photography, cut and paste, 2D and 3D CAD, and technical annotation. It is not necessary to evidence all of these techniques, but a minimum of 2 are required. In product manufacture, students are required to plan, make and test one or more products that match the manufacturing criteria of the task. If a single product is made, it must be manufactured using more than one material and process. And if more than one product is produced, the collective group must contain more than a single material and process. In this section of the portfolio, it is strongly recommended that teachers set the manufacturing tasks in order to ensure that students improve competencies and learn new skills in preparation for A2 tasks. It is a rule that where CAM is used, it must not exceed 50% of product manufacture. When more than one product is made, planning and testing should only be evidenced once. It is a requirement that clear photographic evidence is submitted that shows the quality and complexity of challenge relating to all manufacturing tasks. Work in this section should be presented in A3 format. It is expected that the complete portfolio of creative skills will be presented using 25 to 30 sheets of A3 paper. There is no penalty for exceeding these guidelines. When developing a plan for production, students must plan a sequence of manufacturing operations in an appropriate order. They must also consider time taken for each operation and consider important deadlines. It is important to include detail when specifying manufacturing operations. It is not sufficient to state, for example, cut legs to length or drill holes. More information is required, such as cut 4 legs to lengths of 400 millimeters using a tenon saw, or drill 2 20-millimeter holes using a flat bit and pedestal drill. When suggesting time taken for manufacturing operations, this should be recorded in hours or minutes. Time periods recorded on lessons, weeks, or dates give no indication of how long these periods are in real time. A production plan can be presented in any appropriate form, as long as it contains required information. The slide shows a comprehensive plan for production that includes an appropriate sequence of operations and information on sizes and equipment to be used. Time and deadlines are recorded using a Gantt chart. Quality control checks are specified, which is not a requirement, but good practice in preparation for A2, where quality checks are required. This slide shows an example of a poor production plan, which gives little detail and would be of limited use for a third party trying to follow the plan. Some students include health and safety and justification for the selection of manufacturing materials in this section, which can be credited in making. When demonstrating making skills, students can choose to make a single product or more than one, but they must aim to produce high-quality outcomes that meet the requirements of the manufacturing criteria, fully match the final design proposal in terms of function, sizes, finish, etc., and are appropriate to expected levels of response 1 year on from GCSE. Students must show demanding and high-level making skills in order to achieve the high category of marks in this section. So it is essential that the product under construction offers enough challenge and complexity to allow access to high marks. Where CAM is used, this should be limited to no more than 50% in order to allow students to demonstrate a range of making skills. Over-reliance on CAM limits opportunities to access the high mark range. It is a requirement that students justify their choice of materials for use in making their product. This can be done as part of the diary of making, as separate statements, or as part of planning. It is helpful to moderators if teachers, as part of their annotation, point out where this evidence can be found. As evidence of the quality of manufacture, clear photographs must be submitted that show enough detail to support the credit awarded during centre assessment. As photographic evidence is the only proof of manufacturing quality, it is essential that images convey details of levels of difficulty and complexity of construction, so it is unlikely that a single image will achieve this. A series of photographs, called a diary of making, taken over a period of time during manufacture, is the ideal way of highlighting processes used and providing examples of precision and attention to detail that may not be readily noticeable in a single image of the finished product. It is important when presenting photographic images to ensure that they are big enough to allow a moderator to see details. Fewer larger images are of more help than lots of thumbnail images where detail is difficult to see. The final part of product manufacture is testing, and this should be done using measurable performance-related criteria that should have been set at the beginning of this section. Wherever possible, field trials should be used to test a product's fitness for purpose, and superficial testing should be avoided. Tests to see whether a product is aesthetically pleasing or includes particular named materials or techniques are not valid. Tests should be technical and rigorous. Tests should be objective and describe to say what is being tested, how the test was carried out, and what the results were. Where third-party testing is used, superficial congratulatory statements should be avoided. The same performance criteria should be used in third-party testing as that used by the student maker to ensure objectivity. The slide shows appropriate testing being carried out in realistic situations. It is essential that 3 or 4 measurable performance criteria are set at the beginning of the making task, so that realistic and meaningful testing can be carried out on the finished product to test its fitness for purpose.